What we're going to do today is finish up the last part of the lesson on the Java Executor Service interface. If you recall what we talked about last time, I talked about the more powerful features that the Executor Service provides, the other interfaces and classes it works with. Talked about some of the key methods that the Executor Service interface provides, things like submit and shutdown now, and so on. And you'll have to know how all of those different, or some of those methods work for the next programming assignment, 2A. We'd also talked about the thread pool executor as an implementation of the Executor Service interface. And then the last thing I'll do here is show you an example that illustrates how we can apply the Executor Service interface to implement yet another variant of our PrimeChecker app, which we've been using as the running example for some time. So if you recall, this is this embarrassingly parallel app, and this particular version shows how we can use the Executor Service to determine if n random numbers are prime. As before, you can enter in the number of numbers you want to generate, and then you can go ahead and run the program and change the number and cancel things and so on and so forth. And as always, you can download this at my GitHub account. The other thing that this app version adds to what we had before, remember the first version we looked at was the Executor version, which was very simple, didn't handle many features. This version shows a couple of other things. It shows how to handle runtime configuration changes. So that's an Androidism whereby when you rotate the phone from portrait mode to landscape mode or vice versa, then the current activity is shut down and a new activity is created to handle the different layout. What we want our app to do is continue to run even when the activity is created or destroyed. So we want to kind of decouple the concurrent processing from the UI-related operations in the program. And we'll also show very, very briefly how to handle Java thread interruptions. So if threads are running in the background performing tasks, we can ask them if they wouldn't please mind stopping their computations. We'll cover this in much more detail later, but I'll kind of give you a quick overview of how it works here. As before, as with the first version, we're going to use a fixed size thread pool that's tuned to the number of processor cores on the computing device. And we do that, as you can see here, by saying new fixed thread pool. And that uses the runtime.getRuntime.AvailableProcessors method, which is a Java method that goes and checks to see how many cores the execution environment or the virtual machine thinks it has at its disposal. You can tell that this name, available processors, was written a long, long time ago. Remember, Java came out in 1995-ish time frame, quite a long time ago. And back in those days, they didn't really have multi-core processors. They had multiple CPU processors, or they were basically multi-processor CPUs or multi-processor servers. And so back in those days, the number of processors was the number of processors that were on the computer. Nowadays, it's much more likely to have a number of cores on a given CPU. So they just kind of hijacked that method to return the number of computational elements that are available at the hardware level. By default, the fixed thread pool will use an unbounded queue in order to avoid deadlocks. So it'll just keep allocating memory to put things in the queue, but there's only a fixed number of threads in the pool. So you're kind of trading things off. You're avoiding deadlock and thread pool induced deadlock, which you can read about more at this link, by potentially using an unbounded amount of memory. Now, in practice, is this really a problem? Well, it's possible, but most of the time you will scale your system so you won't have an unbounded amount of work showing up at a server. If you do have an unbounded amount of work, you'll eventually run out of memory if you do it in a naive way. We're also going to have a second thread. So this is the user interface thread that's going to be basically putting things into the thread pool. And then we're going to have a second thread, which is a background thread. And this is going to wait for the computations to finish. So this thread will be feeding work into the queue and then into the queue of callables, which are processed by the threads. And then we'll have a second thread that's going to wait for the results to process the results that come back after things are done running in the thread pool, after we've determined whether a number is a prime number or not. Here's the little helper class called PrimeCallable, which implements callable. Remember, callable is the interface that's defined in the Java Executor framework, the Executor Service framework, in order to be able to do two-way calls. So those are the two-way calls that are going to do some computation and return a result. And prime callable is just an implementation of that interface. The constructor will stash away the prime number candidate. This is the number we're checking to see if it's prime. This is the random number that was generated automatically. And we have the isPrime method. If you remember, that's the one that does kind of the brute force work to see whether or not a number is prime. And then the call method, which is the hook method that the Executor Service framework, or the Executor Service implementation, which would be a thread pool executor, will call back when there's a thread ready to do the work. That is going to turn around, and as you can see, it's going to make a call to isPrime to see if this is in fact a prime number, and it's going to store the result in a new prime result, which we'll talk about in a second, and that prime result will basically deliver back what the original number was, the original candidate. We were checking for primality, and the smallest factor if there is one, or 0 if it's a prime number. So you might ask the question, why do we need to know what the original number was? Well, the way that the GUI is going to work is we're going to end up printing output that says, you know, this number has a smallest factor of whatever. So we need both those pieces of information. So we have to get both of those things back to the caller. And since everything's running asynchronously, we have to store both pieces of information in this prime result tuple. Okay, so that's basically prime callable. As we'll see, prime callable is what's going to be used to get work into the thread pool to run in the background to do the computations. Now, of course, you know, I'm not expecting anybody here ever to have to write a prime factorization or prime number checking app, but the basic principles still apply. You have work to do, you give the work to the thread pool, it does the work, and you get the results back through futures. The way this works is when we go ahead and run all the computations the first time, we're going to end up with a list of futures to prime results. So this is what the UI thread is going to do. The UI thread doesn't do the computation. The UI thread just goes through the list of random numbers, or generates random numbers, and throws them one at a time into the pool of worker threads to do the computation. And the results that come back when we submit the work for running in the background will be a list of futures to prime results. And we're going to initialize this using a Java 8 stream. I think I've shown you this type of code before with the earlier example. So we're going to make a stream of random numbers, and we're going to have count of them, and they're going to range from smax value minus count to smax value. That just makes sure that we have big numbers, and they're going to have a bunch of duplicates because we keep them within a certain range. We then use the map to obj intermediate operation, which is part of the stream framework, and this basically says, take the stream of random numbers, and for each one, wrap each random number up in a prime callable, a new prime callable. And what that's really doing is that's just calling this constructor. So it's making a new object with this constructor for each prime, randomly generated prime number. This is something that's called a constructor reference. If you want to learn more about that, I have some other videos that talk about constructor references. So it's going and making a constructor reference, which creates a new prime callable for each random number. And then we go ahead and take each of those prime callables, which comes out of this operation in the stream, and we go ahead and submit it to run with the Executor Service. So that will go ahead and take each prime callable for every random number and submit it. And remember, what submit does, this is another example of a method reference. This is an example of the method reference, mExecutorService : submit. What this does is it goes ahead and it will submit a two-way task for execution, and it returns a future to a prime result. So that's the pending task results that are going to be running after the computation finishes in a background thread in the worker pool. And then the final thing we do is we take that stream of futures and we collect it into a list of prime results. So obviously we could have written this thing as a loop. There's nothing that would have stopped us from writing this with like a for each loop. But this code I happen to think is a lot cooler and cleaner and more modern functional Java programming. So this is a sequential stream that generates random numbers, turns them into prime callables, submits the prime callables to the executor service, gets back a stream of futures to prime results, and then turns those things into a list. So the cool thing about this is you can kind of read it top to bottom in a very linear way, and once you know how to decipher Java 8 stuff, it's really straightforward to understand. Here's the future runnable. This is the computation that runs in a background thread, and its purpose is just to take all those futures to prime results and basically wait for them to complete. So future runnable implements runnable. It's going to stash away the list of futures to prime callables, which we're going to have gotten, of course, from here, this field right here, futures, or this variable right here. And we have the main activity. That's just so we can display things back in the Android window. Here's the constructor. That goes ahead and takes an activity and a list of futures to prime results and stashes them away. The workhorse method here, as you might anticipate, given that future runnable implements runnable, is the run hook method. So this is the hook method that's called back when the thread, that's the background thread, is going to be created in order to do the computation. What this does is it uses the for each method, which is another Java 8 ism, and it basically says for each future in mFutures, remember mFutures was just this list of futures, for each future in mFuture, take that future and go ahead and wait for that future to complete. And this is an example of synchronous future processing. And what that means is that this call to get will block if the async processing that's taking place in the pool hasn't finished running yet. If the asynchronous processing is done, then get will return right away. But if it hasn't finished, we're going to block. And we'll see that's one of the quirks of the synchronous future processing model. This is a very clever little adapter method that converts something that takes a checked exception, future : get uses checked exceptions, which are the root of all evil in Java 8 programming and beyond, and it converts it through something called exception laundering into a runtime exception. So our code gets cleaner. We don't have to put try-catch blocks here. And so what that'll do is that'll go ahead and get this back as a supplier, and then we can simply get the result. After the future returns, we can get the result here, and that will give us the prime callable, prime result, and then we can check to see whether or not it was a prime number or not. If the smallest factor is 0, it's a prime number. If the smallest factor is non-zero, then it's not a prime number and we have a factor. And then we'll go ahead and display the results through the activity. Okay, so when we're all done processing this entire loop, then we can go ahead and tell everybody we're finished. Now, I mentioned before that one of the cool things about this program is if you rotate the screen, the program, the concurrent processing still continues to run. The previous version that we had, the earlier version, the Executor framework version, the simple one, didn't allow that. If you rotated the phone, it all started over again from scratch, which was kind of it was a waste, because if you were doing long-running computations, you'd like them to continue running whether or not you're rotating the phone or not, because they're really independent of the user interface. So what we do is we have a class called retained state, and you can see that the fields in this class keep track of all the concurrency-related objects. So we have Executor Service, future runnable, the thread. Those things are all stored in this object. And then we can go ahead and create and start the code using the elements of this field. So you can see here that we have mFuture runnable, which is one of those elements, and we make a new future runnable. We go ahead and create a new thread with the future runnable as the argument to the constructor of thread. So in other words, that's the computation it's going to run when it starts up. And then we can go ahead and start it, and that will then run in the background. And this state will be stored in this object called mRetainedState. And what's cool about that is that Android provides these really interesting hook methods. They're rather wordy. It's onRetain non-configuration instance, boy is that a mouthful, and getLast non-configuration instance. So the way this works is that when an object is, or when an activity is first created, it goes and checks to see, did we have any configuration, non-configuration instances lying around? That's just a fancy word for things we want to survive the rotation of the device. And if the answer is no, we did not, we start from the beginning. If the answer is yes, we keep running from where we left off. So this is what's done when we start a new activity. It goes to check to see if this is the second or nth, second or subsequent time the activity started. And whenever an activity goes away, we basically keep this state around, and so we can go ahead and get this state so it can be loaded and stored. So we can get it here when we're going to go to have the activity go away, and this can be used to get it back if it's already been created. That's a little bit of an Androidism, but it's worthwhile to know how this works. Okay, so that's basically the gist of it. Let's talk about how this code compares and contrasts with the earlier version, the very simple Executor version of this app. So a couple things are a win with this approach. If you recall the last approach where we had this, I think we called it prime runnable or something like that, we had to store the activity with the prime runnable object because there was a one-way call. We had to keep the reference to the activity with the computation that was being done in the background so we could get back to it later. And that meant that we had this tight coupling between what we had there was the prime runnable and the main activity. And that complicated a variety of things, not the least of which is runtime configuration changes, because you have to update that activity when your program goes away, when your activity goes away. With the prime callable version and the two-way semantics we have here, we don't have to have that tight coupling anymore, because prime callable doesn't need to know anything about main activity. That's something that can be handled by whoever's processing the futures, which is going to be the main activity. So it doesn't, or the thread that's running in the context of the main activity. So that's a lot cleaner. So this code is cleaned up. Another nice thing we have is we have support for lifecycle operations. So if you recall last time, there was no way, once we kind of set everything running with the Executor version of the app, because it only has one method called execute, there's no way to terminate the executor, nor is there any way of canceling the existing things that are running, at least not easily. So what we do here is we have a method called interrupt communications, and this method is connected with this button push. So once you start running the app, the little start button turns into a cancel button. Very common technique with floating action buttons in Android. If you have something that's a start button and you click it, it'll change its shape, it'll change its icon to be the cancel button or the halt button. And so when you click this button, that goes ahead and calls this method, and what this does is it shuts everything down. So as you can see, what it does is it goes to the Executor Service, which we stashed away in our retained state, and it says shut down now, which is basically a non-graceful shutdown. It just says, I don't care what the heck you're doing, shut yourself down. Now again, the threads that are tasks are welcome to ignore that, but we'll see that ours don't in a second. The next thing we do is we go ahead and say to that background thread, shut yourself down too. I want to interrupt you, so don't do any more processing. And then, remember this is the main thread of control, the UI thread. Then we say, let's wait for all this stuff to shut down, and we're going to wait up to 500 milliseconds. And luckily 500 milliseconds isn't too long. It won't cause a application or activity not responding or application not responding exception. It's relatively short, but it'll give us a chance to kind of wait for everything to shut down. And that way we can kind of be confident that by the time this program shuts, we've killed all the threads that are running around in the background. So this will interrupt everybody who's doing stuff. Here's how we handle this in the isPrime method. So the isPrime method is going to put this new little check in here. So before, what isPrime did was it just sort of went through cranking away, trying to see if there were any factors for this prime candidate. In this case, we add an extra check to say, have we been interrupted? And if we have been interrupted, then we go ahead and shut ourselves down. So the nice thing about this is when someone rotates the phone, we can shut things down in a variety of different ways. We can click a button to shut it down. That'll shut it down, so it won't end up causing problems. Okay, any questions about that? So that's the way you would do this. The code over here interrupts threads, either by shutting down the executor service or interrupting the background thread. And then this is an example of how we check for that and handle it by breaking out of our loop. Because otherwise this could run for a long time, because checking for a big number, checking whether a big number is prime is expensive if it's prime. It takes a while. However, as with everything, there's still some limitations with what we've described here. So one of the problems here is that this call to get will block as long as the computation that's associated with this future is still running in the background, and especially if it's a really long-running computation, like it's checking for the primality of a big number, it's going to take a while. So this may not be the most efficient way to wait for results, because we're kind of at the mercy of the order in which we wait for them, which isn't necessarily good. So this call may block on that future, even if other futures have already completed. We're going to have to wait their turn to check them later. So this guy's going to kind of clog everything up. Here's a simple example of this. This is what's sometimes referred to as head-of-line blocking. And head-of-line blocking is something you see in a variety of contexts. One context would be if you're going through a drive-through at a fast food restaurant, and so you've got a line of cars that are waiting to pick up their food, and if the person ahead of you in line has some really complicated order, then you've got to sit there and wait for their order to be fulfilled, even though you may just want to get a drink, right? Your order may take no time at all to fulfill, but if the person ahead of you is doing something complicated, you've got to wait for them. So that's called head-of-line blocking. And there's lots of other examples of head-of-line blocking as well, but that's one. Another problem here is that the isPrime method is coupled with PrimeCallable, and that means that, first of all, we can't easily change this method to do a better implementation without doing a lot of surgery to our code. And number two, even if we already know whether a given number is prime or not, this guy is still going to crank away and recheck it. So remember our code that we generated the random numbers tried intentionally to have a bunch of duplicates? So if we already have figured out that some big number's prime or not, then wouldn't it be faster to just return the result that we'd pre-computed and cached away, rather than having to go through the laborious process of trying it all over again? So we're going to show how to fix this in some upcoming lessons, one of which will be Java Future Task, where we're going to apply something called memoization in order to fix that problem. Okay, so that's the end of the example portion of the Java Executor Service.